Hello students, I am Saili Rathod and this is the video number 7 of the video lecture series of electrical measuring techniques. In today's video, we will cover the topics that is essentials of measuring instruments, deflecting, controlling and damping torque, its working and equations. Okay, so today's topic is a second part of the first unit, as we know that the first unit consists of 3 parts. So second B part is started in today's video. Okay, so let's start with today's topic. Here you can see the contents that we are going to cover in today's video lecture. In order to ensure proper operation of indicating instruments, the following 3 torques are required. Okay, now why we are going to study these 3 torques? We are going to study the essentials of measuring instrument. Means what are the basic requirements of the measuring instruments and what is the essential part of that instrument. So the torque is a very essential part of any measuring instrument. That's why we are going to study 3 types of torques: deflecting, controlling and damping torque. In this also there are some types of torque. Like in controlling torque, there are 2 types of torques: spring and gravity control, that we will see in the upcoming slides. So this is the basic content which we are going to cover in today's lecture. Before moving ahead in these 3 types of torques, we will see what is the basic concept of the torque. Okay. So what is torque? Torque is the measure of the force that can cause an object to rotate about an axis. Now, what is the need to rotate any object about an axis? As we are going to study the electrical instruments, measuring instruments, in which the indicating instruments are having a pointer which is going to move from 0 to the particular magnitude. So for that purpose, to move that pointer, there is a need of rotation of that pointer around a particular axis. So for that purpose, we need a particular force which can cause that object to rotate about a particular axis. So that's why we need to study the torque. So I think the basic concept of the torque is clear to every student. The second point is, force is what causes an object to accelerate in linear kinematics. As the force, it causes the object to accelerate in linear kinematics, means in linear direction. Similarly, torque is what causes an angular acceleration, means it will cause the pointer to move around a angular acceleration. Hence, torque can be defined as the rotational equivalent of linear force. Now, the basic concept of the torque is clear to everyone. Now we will move ahead with the types of torque which are required for the measuring instruments. Now the first type is deflecting torque, second is controlling, third is damping torque. So all these torques are needed for basically the indicating instrument, where the scale, the pointer is used to indicate something or some value on the scale. So first one, deflecting torque. What is deflecting torque? Deflecting torque causes the moving system and pointer of the instrument to move from its 0 position. As we know, as this, consider this is a scale and this is a pointer. So this pointer will move from 0 to a particular direction. So for this purpose, we need a torque which is a deflecting torque, which will deflect the pointer from its 0 position. This is the first type. Then second one is the controlling torque. Now, as from the name itself we can see deflecting torque means what? It allows or it causes the pointer to move or to deflect. Now second one is controlling torque, means it allows the pointer or it causes the pointer to move, but it also controls the pointer. So controlling torque limits the movement of the pointer. This is the main function of the controlling torque, that is to limit the movement of the pointer and to ensure that the magnitude of deflection is unique and is always same for the given value of electrical quantity to be measured. It means wherever any quantity is electrical quantity is measured on a particular measuring scale, the controlling torque, what it does, it ensures that the magnitude of deflection, means for a particular current, for example, if a 1 ampere current is indicated on that instrument, then the controlling torque ensures that the pointer should show 1 ampere current on the scale for every time whenever 1 ampere current is measured on that scale. So the two functions are to limit the movement of pointer and to ensure the magnitude of deflection is unique and it is same for the given value of electrical quantity. This is the controlling torque. Now the third torque, that is the damping torque. Damping torque minimizes the oscillations of the pointer about the final steady state deflection and makes it steady. As we know, on a particular any measuring scale, the pointer will move from 0 to a particular value, and when it fluctuates on that scale, there may be possibility that the pointer will not get steady on a particular value. It may get it may be show fluctuations, it may be showing the fluctuations continuously. So to avoid these fluctuations of this pointer, the damping torque is used. Damping torque, which minimizes the oscillations of the pointer, means it will not oscillate around a particular value, it will get steady on the particular reading. So this is the third type of damping torque. First one, deflecting torque, which causes the movement of the pointer. Controlling torque, which controls or limits the movement of pointer, and damping torque, which minimizes the oscillations of the pointer. These are the three types of torque. Now in today's lecture we will see these two torque in detail, and in the next lecture we will see the third, that is damping torque. As this is a wide topic, so it will need some time, so we will cover only two torques in today's lecture. So here we have seen the essentials of indicating instrument. Now we have seen the three types of torque, but why do we need these torques? So first point is, indicating instruments are those which indicate the value of quantity that is being measured at the time at which it is measured. Second point is, such instrument consists essentially of a pointer which moves over a calibrated scale and which is attached to a moving system pivoted in bearing. Okay, it means indicating instrument which will give the output on a particular scale. So the pointer should be moved from 0 to a particular value. So this pointer is attached to a moving system pivoted in bearing. Bearing, why? Because we need to rotate it in a angular momentum or angular acceleration. So this is the need of indicating instrument. The moving system is subjected to the following three torques as we have seen early. First one, deflecting torque, or it is also called as operating torque. Second is controlling or restoring torque, and third one is damping torque. So these are the essentials of indicating instrument. Now we will move ahead with the first, that is deflecting torque. So in the previous slides I have already discussed about the deflecting torque and what is the need of deflecting torque. So the basic idea must be clear to everyone. Now we will see the next point. The deflecting torque is produced by making one of the magnetic heating, chemical, electrostatic and electromagnetic induction effect of current or voltage and cause the moving system of the instrument to move from its zero position. Okay, so here some effects are shown like magnetic heating, chemical, electrostatic, electromagnetic induction. So all these effects will work as a deflecting torque and it will cause the moving system to or the instrument to move from its zero position, means it will start deflecting the pointer from its zero position. So this is the deflecting torque. Second point is the magnitude of the deflection force depends on the value of electrical quantity to be measured. So the magnitude of the deflection force means how much the pointer should move from zero position. It depends on what? It depends on the electrical quantity which is measured, means the input. If the input is high, the deflection is also high. If the input is very low, the deflection will be less. Then the method of producing this torque depends upon the type of instrument. Okay, so this is about the deflecting torque. Second one is controlling torque. The magnitude of the moving system would be somewhat indefinite under the influence of deflecting torque unless the controlling torque existed to oppose the deflecting torque. Okay, so unless the controlling torque existed to oppose the deflecting torque, up till this stage the magnitude of the moving system should be controlled. So for this purpose we need a controlling torque, means the main function is to control the movement of the indicating pointer. This is the main function. It increases with increase in deflection of moving system. The torque increases when the deflection is increased, and under the influence of controlling torque the pointer will return to its zero position on removing the source producing the deflecting torque. Okay, so it is but obvious in any measuring instrument when you remove the input the pointer should come down to zero. For an example, in your vehicle, two-wheeler or four-wheeler, the speedometer it changes the magnitude of the pointer from 0 to 40, 50, 60, 80, whatever it is the speed of the vehicle. But when you stop the vehicle, the pointer comes down to 0. Why this happens? This is due to the controlling torque. The property of that instrument should be like this, that the pointer should come down to 0 after the input is removed. The fourth point is, without controlling torque, the pointer will swing at its maximum position and will not return to 0 after removing the source. Okay, so if we have not applied the controlling torque, the pointer will swing at the maximum position, means if the vehicle is in speed of 80 kilometers per hour, then the pointer will fluctuate or it will oscillate around the same speed even after your vehicle is switched off. So this will happen if the controlling torque is not applied. So this is about the controlling torque. Here we have seen the pointer is brought to rest at a position where the two opposing forces, that is deflection and controlling forces, are equal. Now we will see two types of control systems. Okay, so in controlling torque there is a need to control the pointer. For that purpose two systems are used, spring control and gravity control. As the name itself shows, spring control, it uses a spring to bring down the pointer, and gravity control, it uses the force of gravity to bring down the pointer. So first one, spring control. In this diagram we have shown the spring control, where the two springs are used, A that is control and B that is spring, and this is the pointer which is pivoted around the bearing and the axis, and this is your scale. Suppose this is your scale and the pointer is moving from 0 position to upward. Okay, so this is controlled by the spring. Here the spring B is shown here. So this diagram is explaining the concept of spring control. When the pointer is deflected, one spring unwinds itself while the other is twisted. Okay, so two springs are there. When one spring is unwinds itself, means if spring A is unwinding itself, the other spring will be twisted around in the other direction. This twist in the spring produces restoring, means the controlling torque. This twisting of the springs, what it will give us, it will create the controlling torque which is proportional to the angle of deflection of the moving system. Angle of deflection, that is theta. So this angle of deflection is directly proportional to the restoring or controlling torque. This we will see in this slide. Here angle of deflection, that is theta. We have seen some basic equations of the spring control. Scale of spring control type instrument is uniform. TD is directly proportional to I, means deflecting torque is directly proportional to I, that is current. And also we know that controlling torque is also directly proportional to theta. Why it is directly proportional? Because angular deflection, if the angular deflection is increased, the torque, controlling torque, it also increases. So both these quantities are directly proportional. At final deflection or steady state position, TC is equals to TD. Okay, means at the final deflection both these torques will be equal. So from this equation we can say that theta is directly proportional to current, means the angular deflection will increase as the input current is increased, and the angular deflection of the pointer will decrease if the input current is decreased. So the angular deflection is directly connected with the current, means directly related to the current. Now moving ahead with the gravity control. As in the previous spring control, the pointer was controlled by the spring, and here the gravity control, the concept of gravity is used. So to apply the concept of gravity, we will need some weight to be connected to the system. That we will see in the next slide. In gravity controlled instrument, a small adjustable weight is attached to the spindle of the moving system such that the deflecting torque produced by the instrument has to act against the action of gravity. Okay, so small adjustable weight which is attached to the spindle means the weight will be acted against the deflecting torque. Second point is, thus a controlling torque is obtained. This weight is called a control weight. Another adjustable weight is also attached in the moving system for zero adjustment and balancing purpose. This weight is called the balance weight. It means we have used two weights, that is one is control weight and second one is balance weight, W1 and W2. Two weights are used for the gravity control, which we will see in this diagram. Here you can see this is the pointer. Here we have shown the angular deflection theta. This is a pivoted spindle, means at this point the pointer and both the weights are attached. Here two weights, that is W1 control weight and second one is balanced weight. Two weights are used, and this weight, the angular deflection will have to work against these two weights. Okay, Now the angular deflection theta, we have shown here that W1 cos theta in this direction and W1 sin theta. This we will need wherever the angular deflection is to be calculated. So just remember the basic concept. In gravity control, two weights are used, W1 control weight and W2 balance weight. And against this weight, the angular deflection will be applied. Now, in this, a small adjustable weight is attached to the moving system pointer in such a way that in deflection condition, it produces a restoring or controlling torque. So W1 provides the controlling torque and W2 is for balancing the weight of the pointer. These are the two functions of both the weight that we have seen in the previous diagram. Now TC, that is controlling torque, is equals to W1 sin theta into L. Okay, so sin theta means angular deflection theta. We have to multiply W1 sin theta and L, which will give W1 L sin theta. So controlling torque, it is directly proportional to sin theta, as we have considered the W1 and L as constant. Okay, so as we know, weight and the L, both these quantities are constant, so we can write TC is directly proportional to sin theta. Okay, now we know that deflecting torque is directly proportional to current, as we have seen this in the previous torque equations. So at steady state position, deflecting torque is equals to controlling torque. We know that deflecting torque is equals to controlling torque. So we can say the right hand side of the above two equations. From this we can write I is directly proportional to sin theta. So the scale of the gravity control type instrument is non-uniform. Okay, so this is a very basic equation where we have proved that I is directly proportional to sin theta. Now here we will compare two types of control, that is spring control and gravity control. So first point is, this is very important question. It may be asked in your exam, that is what is the difference between spring control and gravity control. First one is, increase in torque is much faster as the controlling torque is proportional to the angular deflection. Okay, as we have seen in the equation, that is TC is directly proportional to theta. So the speed increase in the torque is faster as compared to the gravity control. So first point in gravity control is the controlling torque increases very slowly as it is proportional to sign of angular deflection. Hence scale is more cramped at the lower end. Okay, in spring control we have seen the equation TC is directly proportional to theta, but in gravity control we have seen that the TC is directly proportional to sine of angular deflection, means sine theta. So the speed of gravity control, movement of that pointer, is very slow. Second point is, this type of instruments can be caused in both vertical and horizontal positions, used for panel board, meters and lab purpose. And the gravity control, this type of instrument can be used in vertical position only, thus suitable for panel boards only. As in the gravity control, we use the concept of weight and the gravity. So it is compulsory to hold the instrument in vertical position. Third point is, they need not be leveled before being used. And this kind of instrument should be properly leveled before being used. Otherwise, zero error may occur. Okay, so as spring control, it does not relate with any gravity concept, so you can use the instrument anyway, but in gravity control the instrument should be leveled properly. It should be kept on a proper leveled base. This is the third point. And fourth point is, it is comparatively higher in cost and the gravity control is less in cost. Okay, so this is the basic difference of spring control and gravity control. So both these control systems are a part of controlling torque. Okay, now third torque is damping torque. As we have discussed it early, that what is actually the damping torque. So we will discuss all these things in the next lecture. Just we have given an overview of the damping torque.